studying in Sri Venkateswara College of Engineering, Bangalore. Today I am going to discuss about the operation of mass transistors in accumulation, depletion and inversion mode and the steps involved in Nmos fabrication. Operation of mass transistors in accumulation, depletion and inversion mode. Mass means metal oxide semiconductor. Transistors are fundamental components of modern integrated circuits, commonly used in digital logic gates and analog amplifiers. They operate in three different modes: accumulation, depletion, and inversion mode, depending on the voltage applied to the gate terminal and the resulting charge distribution within the transistors. Mass transistors in accumulation, depletion, and inversion mode. First one is accumulation mode, second one is depletion mode, and third one is inversion mode. Accumulation mode. In accumulation mode, the voltage applied to the gate terminal is such that it attracts free electron from the semiconductor substrate towards the surface beneath the gate oxide layer. This creates a layer of excess electrons on an electron accumulation region just below the gate oxide. The presence of electron accumulation layer forms a conductive channel between the source and the drain terminal of the mass transistors, allowing current to flow from the source to drain. This mode, the mass transistor is on and it conducts current easily. It typically used to operate with a positive gate source voltage VGS. In depletion mode, the voltage applied to the gate terminal is negative, but not strong enough to invert the channel. Instead, it creates a small region of depleted charged carriers beneath the gate oxide. The depletion region reduces the conductivity of the channel, making it less conductive compared to the accumulation mode. Depletion mode mass transistors are not commonly used in digital applications but can be found in some analog circuit designs. They operate with a negative gate source voltage. Inversion mode. In inversion mode, the voltage applied to the gate terminal is sufficiently negative to attract charge carriers and holes for P channel and create an inversion layer just beneath the gate oxide. The inversion layer forms a conductive channel between the source and the drain terminal, enabling a high flow of current. Inversion mode mass transistors are most commonly type used in digital logic circuits. They operate with a negative gate source voltage VGS for N channel mass transistors and positive VGS for P channel mass transistors. Today, next topic, I will discuss about the steps involved in Nmos fabrication. The fabrication of Nmos means N-channel metal oxide semiconductor transistors is a complex process that involves multiple steps in semiconductor manufacturing. Here I will outline the key steps involved in the fabrication of Nmos transistors. Sub First one is substrate preparation. This process begins with a silicon vapor which serves as the substrate. The vapor is typically made of single crystal silicon and it is highly polished to provide a clean and flat surface. These are the diagrams used in the fabrication process of Nmos transistors. Next is thermal oxidation. A thin layer of silicon dioxide known as the field oxide. It is grown on the silicon vapor surface. This oxide layers insults region where transistors will be built and defines the active areas. Photolithography. Photolithography involves applying a layer of photoresist material onto the vapor surface. A mask is used to project a pattern onto the photoresist. This pattern defines the location of the various transistors components including the mass transistors. Exposure and development. A vapor of exposure to ultraviolet light through the mask. The areas exposed to light become more or less soluble depending on the type of the photoresist used. Next one is etching. Etching is used to remove the silicon dioxide in the areas not protected by the remaining photoresist. This step defines the active regions where transistors will be built. Ion implementation or doping. To create the N-type region for Nmos transistors, ion implementation is performed. This process involves the introduction of specific dopant atoms into the silicon substrate to modify its electrical properties. Next step is thermal annealing. The vapor is subjected to high temperature annealing process to active and redistribute to the dopant atoms, ensuring the desired electrical characteristics in the N-type regions. Next one is gate oxide growth. A thin layer of silicon dioxide is grown or deposited on the vapor surface. To serve as the gate oxide, this oxide will be separate the gate electrode from the silicon substrate. Photolithography and etching. Photolithography is again used to define the shape of the gate electrodes or the polysilicon layer. Etching is performed to remove the excess polysilicon leaving behind the gate surface. Source and drain formation. Using photolithography, ion implementation, and annealing, N-type regions are created in the silicon substrate and either side of the gate to form the source and drain regions of the Nmos transistors. Interconnection. Next step is interconnect and metal layers. Additional layer of insulating material and metal are deposited on the pattern to create the interconnections that connect transistors and their components in the integrated circuit. Next is passivation and testing. The final step involved in is passivation layer to protect the fabricated components and extensive testing to ensure the functionality and equal quality of the integrated circuit. These steps provide a high level of overview of the Nmos fabrication process, which is complex and highly precise manufacturing process used in the production of semiconductor devices like microprocessors, microchips, and various other integrated device circuits. Thank you.